So welcome back and welcome to this last session with me conducting the session. But now after this, you will be conducting the session, you people, together with my teaching associates. And those sessions will be in the next week, right? And you and the teaching associates together will be conducting the remaining sessions in my course, in my part of signals and systems, right? So in this last session, I have two objectives. The first is to again discuss some part of the generalization of transforms. I was talking about the Laplace transform in the previous session, and in this session I am going to talk about the Z transform and the discrete time Fourier transform. Let's talk about the discrete time Fourier transform first. Now yesterday we saw that you can sample a signal, right? So when you sample a signal, you get a stream of samples. Now what is the idealization in sampling? What is the ideal form of sampling? This is something we must, what is idealized sampling? Idealized sampling means multiplying the signal with a train of impulses, right? So it means multiplying, so there's a continuous time signal, xt is a continuous time signal. We multiply xt with a train of impulses. Let us sketch. So you have this signal x of t, and you have this train of impulses spaced by uniform train of impulses, spaced by Ts between them. When you multiply xt, a continuous time signal, by this uniform train of impulses, what is the consequence? Each of these impulses effectively gets multiplied by the value of the signal at those points. So each you see, we now invoke the shifting property of the impulse. What does each impulse do? It shifts, chanta hai, it shifts the signal, and it picks up the value of the signal at that point, right? So this becomes summation. So there was a continuous time signal multiplying a train of impulses. Now the samples of the signal come into the summation. So you get n going from minus to plus infinity, x at nts So now you have only, so when you multiply a continuous signal with a train of uniform train of impulses, or even if it's non-uniform, only the impulses survive appropriately scaled. The signal otherwise gets destroyed. Now, what one tutorial exercise which you will be doing, right, in the sessions, and my teaching associates will help you do it, right? One tutorial session. When you conduct tutorial sessions next week, in fact, ideally one of you should try and solve this in front of the class, and my teaching associates will help you do it. But still, one such tutorial will be on module 3, and it will be the following. Obtain the Fourier transform of this product, which means you assume that you know the spectrum. Spectrum is another name for the Fourier transform. So, you know the spectrum of x of t, and you know Ts, you know at what rate you have sampled the signal, ideally, right? Find out the spectrum of the sampled signal. Now, you see, yesterday what we did was to explain the principles of sampling by starting with a sinusoid informally. And we, of course, informally came to certain conclusions about the requirement of sampling rate and so on. But the intent of this tutorial problem is to give you a formal proof of the Nyquist sampling theorem. Is that right? So, my teaching associates will help you, but you should try and do it, and then with the, and in fact, I would expect one or two of you to come forward and teach all of the rest of you the solution to this problem. Namely, you have x of t, you know the spectrum of x of t, and you're required to find the spectrum of this product, the product xt multiplied by this uniform train of impulses. Okay? And then, the next part of the tutorial is thus derive the Nyquist sampling theorem formally. Okay. Anyway, suppose we have this uniform train of impulses. Okay. Let us find out the Fourier transform of this train of impulses. The uniform train of impulses, but now we are going to take the Fourier transform of that train of impulses, where the impulses have been scaled by the appropriate values of the function at those points. So, let us find out the Fourier transform of this. I will call this x sampled t, xst. So, I am finding the Fourier transform of xst. Well, it's very simple, summation n going from minus to plus infinity, x nts delta t minus nts e raised to the power minus j omega t dt integrated over all t. Now, what's going to happen? See, x of nts is a constant. This is an impulse. These are different impulses located at different points, t equal to nts. What will these impulses do? They'll pick up the value, the value of the continuous function around them, right? So, what would this, instead of this summation, instead of this integral, it will simply become a summation. Summation n going from minus infinity to plus infinity, x nts e raised to the power minus j omega nts. Is that right? Simply picks up the value of the continuous function. Let's denote x of nts by x square bracket n. We'll assume that ts is in the background. We know the value of ts. And let us rewrite this. This is summation n going from minus to plus infinity, x of square bracket n e raised to the power minus j. Now, omega divided by 1 by ts, we will write it like that, and n. So, instead of writing capital omega tsn, we will write omega divided by 1 by ts. Now, what is the meaning, what is the interpretation of omega divided by 1 by ts? Omega divided by 1 by ts is a normalized angular frequency. It's a normalized angular frequency. Yeah. Yes, 1 by Ts को आप Fs लिख सकते हैं. Yes. Right. So it's easier to appreciate this, isn't it? You can say omega divided by Fs. Now, you know, we often denote this by small omega. It's the normalized angular frequency. And let us see some properties of this normalized angular frequency. In fact, first let's, you see, this can be rewritten as summation n going from minus to plus infinity xn e raised to the power minus j omega n, where omega is the normalized angular frequency. And we will use a notation for this. You see, you have x of square bracket n. We'll say that x of square bracket n is now a discrete sequence. It's a discrete sequence obtained by sampling the continuous function xt. Is that right? This is called the discrete time Fourier transform. So this is the DTFT, discrete time Fourier transform of the sequence xn, what you obtained here, right? And it's a function of small omega. Equivalently, it can be thought of as a function of e raised to the power j omega, right? So we can think of this as a function of e raised to the power j omega, and the reason is very simple. So if you replace omega by omega plus 2 pi, what do you get? You get summation n going from minus to plus infinity xn e raised to the power minus j omega plus 2 pi into n, which is summation n going from minus to plus infinity xn e raised to the power minus j omega n into e raised to the power minus j 2 pi n. Now, how much is e raised to the power minus j 2 pi n? Remember, n is an integer. 1. Right? So, this is always 1. And therefore, when you replace omega by omega plus 2 pi, you always get the same expression. That means this expression is periodic in small omega with a period of 2 pi. And therefore, it's also valid to think of it as a function of e raised to the power j omega. Because e raised to the power j omega is periodic, with period 2 pi. Now, in fact, this is not surprising. And in fact, when you solve the tutorial problem I've given you, and when you look more deeply at the answer to the question which I posed for you, you will realize that when you sample a signal, what happens is that you get a periodic spectrum. And the periodic spectrum comes by summing up all possible shifted versions of the original spectrum, shifted by multiples of the sampling frequency. And that brings a periodicity on the actual angular frequency axis. It brings a periodicity of, the sampling angular frequency, 2 pi by Ts or 2 pi Fs. And on the normalized angular frequency axis, it brings a periodicity of 2 pi. All right. So this periodicity comes because of the process of sampling. The very process of sampling brings periodicity. Now, there's another way to look at what we have done. Here we started from a continuous signal, we sampled it and found the Fourier transform. But you can associate, what this indicates is that you can associate the notion of a Fourier transform even with a sequence. And that is called a discrete time Fourier transform. So, you can either think of the discrete time Fourier transform as essentially the Fourier transform of a sample signal, or you could think of it as the Fourier transform of a sequence. Either way is all right, depending on the context. Yeah. Now, you see, again, we can ask the same question that we asked for the Fourier transform. Do all sequences have a discrete time Fourier transform? Well, let's see. Let's take the sequence xn equal to half an exponentially decaying sequence, half to the power of n un. So, un is the unit step sequence, not unit function, unit step function, unit step signal. Un is equal to 1 for all n greater than equal to 0 and 0 for all n less than 0. Let us find out the discrete time Fourier transform of this sequence. It's very easy. So, DTFT would be, now we denote the DTFT of x by capital X, and the argument will be e raised to the power j omega. X as a function of e raised to the power j omega is summation. Now, its un goes only from 0 to infinity. So, half to the power of n e raised to the power minus j omega n. So, we can simplify this. Now, is there a way we can find out this infinite summation? It's a geometric progression, right, with a common ratio of half e raised to the power minus j omega. When will this geometric progression sum to a finite quantity? It would sum if the magnitude of the common ratio is less than 1. Let's look at the magnitude of the common ratio. It's a geometric progression. The common ratio is half e raised to the power minus j omega. Magnitude of the common ratio is obviously half. And therefore, this summation is convergent. And therefore, you can find the sum is 1 by 1 minus half e raised to the power minus j omega. This is the discrete time Fourier transform of the sequence half to the power of n un. Yes. It's a good question. Let me, Can you repeat the, yes? When you take the discrete, can you repeat your question? Yeah. Okay, all right. Okay, that's a good question. So, the question is, when you take, you have a discrete sequence x of n. When I take its discrete time Fourier transform, it's a function of small omega. Is it a continuous function of omega or a discrete function of omega? Is that your question? No. So, in the time domain, the sequence is discrete. The signal is discrete because you have sampled it, right? Well, yes. So the question is what is the duration of xn? The duration of xn can be infinite. The duration doesn't have to be limited, but it's discrete. The sequence it's a discrete sequence, right? It's not a continuous time signal, right? And you're trying to bring out the idea of a Fourier transform for sequences or a Fourier transform for sampled signals. But the sample signal could extend to, it could be infinitely long. It doesn't have to be finite in length, no. Right? However, what should be noted is that, also the other question that can come up at this stage is, this is a discrete sequence. Its discrete time Fourier transform is a function of small omega. Now, small omega is a continuous variable. but there is a periodicity. So, you don't have complete freedom all over the omega axis. It's a continuous, omega is continuous. But you see, there's a periodicity of 2 pi. So, on the omega axis, there's a periodicity of 2 pi. And that's why it's unlike the general Fourier transform where you have no periodicity in general, right? And that the loss of that freedom comes from the fact that you're dealing with a sampled signal as opposed to a continuous signal. So, in a sampled signal, the degrees of freedom are less because you have the freedom only to specify the value of the samples. You don't have the freedom to specify the whole signal, right? And therefore, you have lost some freedom, and that freedom is lost by moving from an aperiodic Fourier transform to a periodic Fourier transform. Is that right? So, now this sequence of course has a discrete time Fourier transform, and you know the discrete time Fourier transform. Now, again the same question that we had for continuous time signals can be raised in the context of discrete time signals. Do all discrete time signals have a discrete time Fourier transform? Unfortunately not. Let's take an example again. So, if you now take an exponentially growing sequence, take x of n equal to 2 to the power n un. It's an exponentially growing sequence. Okay. Well, then do we have a discrete time Fourier transform here? Let's see. Suppose you tried to find its discrete time Fourier transform. What expression would you write? The so-called DTFT should be summation n going from 0 to infinity 2 to the power n e raised to the power j omega minus j omega n, which is summation n going from 0 to infinity 2 e raised to the power minus j omega to the power n. Now, this is again a geometric progression. What is the common ratio of the geometric progression? It's 2 e raised to the power j omega minus j omega. And is this geometric progression, is this geometric series convergent? No, it's not convergent because the common ratio has a magnitude more than 1. So, this common ratio has a magnitude more than 1. So, this is divergent. So, what do? We employ the same strategy as we had for the Laplace transform. What was the strategy? First, arrest the growth. First, arrest the growth of the sequence by multiplying it by an exponentially decaying sequence, and then take its discrete time Fourier transform. Is that right? So, and that's how we generalize. So, to generalize, we first arrest the growth by multiplying by r to the power n minus n. For appropriate r greater than 0. And then take the DTFT. Yes? 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 Oh, so okay, that's an interesting question. Are you asking historically? Frankly, I don't know which. It's like this. So, the question is, historically, was the Laplace transform always thought of as a generalization of the Fourier transform? I am not quite sure, I'll have to check. Well, the Laplace transform, anyway, both the Fourier transform and the Laplace transform are named after the mathematician scientists who came up with them. Now, in a way, the Laplace transform was used to solve differential equations as well, but it's not clear to me whether, this came always as a generalization of that, right? Now, you can also think of the Laplace transform independent of the Fourier transform. One can think of it that way, right? And use it to solve particularly what you call linear constant coefficient differential equations, right? However, today when we look at a course on signals or signals in systems or signal processing, I think it is useful to think of the Laplace transform as a generalization, right? Again, there I must give you a word of caution. Actually, it's a very good question, because towards the end of the previous session, I left you not with an answer but with some confusion, isn't it? Now, in fact, that confusion, if you take it further, will illustrate also these boundary cases, where you have a Fourier transform, but if you want to generalize to a Laplace transform, then you have to generalize the notion of the Laplace transform. So I kept you that confusion, because that is, it's a little beyond the scope of what a first course in signal and systems would deal with. But there are these boundary cases. In fact, if you take the ideal filters, the ideal filters obviously are associating a frequency response with them. But the question is, if you look at the impulse response of those filters, strictly speaking, that impulse response should not have a Fourier transform, right? But then you are associating a Fourier transform with it. So, if you are associating a Fourier transform and the Laplace transform is a generalization, then you should also have a Laplace transform for it. What is its Laplace transform? These are questions that would come up when you go deeper. But I didn't want to start dwelling on those questions, but I left you with a confusion at the end of the previous session, actually for those of you who would want to think further, to address these questions which you are asking, right? Should you always think of the Laplace transform as a generalization of the Fourier transform, or should you occasionally look at them independently and see them in their own light? Yeah, so I'll leave it at that. I won't take it further. I'll encourage you to look more deeply at that. Right? Anyway, so let's take this further. So you arrest the growth by multiplying by r to the power minus n for appropriate r greater than 0, and then take the DTF. So let's do that. So you have 2 to the power of n un, okay. Now arrest the growth. So multiply it by r to the power minus n, and now take the DTFT. So it will be summation n going from 0 to infinity to r inverse to the power n e raised to the power minus j omega n, summed from 0 to infinity. Now this is a very easy summation, and we also know what value of r we should choose. So here the common ratio is 2r inverse. And the common ratio magnitude needs to be less than 1, which means r must be greater than 2. Is that right? If r is greater than 2, the exponential growth is arrested. And now you can sum this. And what is the sum? The summation is, you see, here again, we will now replace r e raised to the power j omega by a variable z. It's a complex variable. And this becomes summation n going from 0 to infinity to z inverse the power n, which of course you can easily sum. 1 by 1 minus 2z inverse. But what is the restriction? R must be greater than 2. What is R really? R is the magnitude of Z. R is the magnitude of Z. So here our concern is with the magnitude of Z. The angle of Z has no role in conversions. Is that right? And this is called the Z transform. Of 2 to the power of n un. So you can think of the Z transform as a parallel to the Laplace transform for discrete sequences. Just as the Fourier transform generalizes to the Laplace transform for signals which don't have a Fourier transform, similarly the discrete time Fourier transform generalizes to the Z transform for sequences which don't have a discrete time Fourier transform, right? And of course, it has a region of convergence. So let us sketch. The Z plane is the complex plane, right? Now we wish to sketch that region of convergence. Now R, every value of R, it gives you a contour. The constant R contour is essentially a circle centered around the origin, right? So take the circle with radius R centered at the origin. So here, if you take the circle R equal to 2, then the region of convergence is to the exterior of this circle. This is the region of convergence. So just as the Laplace transform has a region of convergence, the Z transform also has a region of convergence. Now here again, you would want to ask the same question. Is the region of convergence necessary to define simply because you have to worry about the convergence of the expression, or does it also resolve an ambiguity? So it also resolves an ambiguity. So would some of you like to volunteer to tell me what kind of ambiguity is resolved when I say mod Z is greater than 2 there? Or in other words, for the same expression, 1 by 1 minus 2 Z inverse, is there another sequence which has this expression but a different region of convergence? Yes? Very good. Yeah, so we'll invite Bikash again to come and solve. Yes. Or anyone, any other volunteer? Any other volunteer? Now I guess many other volunteers must have got ready. You can come? Yeah, very good. Yes.
Yeah, as we found in case of the Laplace transform, that is for the same function in the S domain, we are having two different inverses. One was happening for S greater than 4 and another was having for S less than 4. So in this case also, whenever it is given like this 1 by 1 minus 2 Z inverse like this, so this is having for this is R is equal to Z less than 2, sorry, greater than 2. So this is a sequence. If we take inverse, then we are going to get this sequence 2 raised to n un. Okay. So this is a causal sequence. Now for the same thing, the ambiguity is the same Z transform will be having, if we take inverse, there will be another region, there is another signal in the n domain, that is discrete domain, which will be having the same kind of transform in the Z domain but for a different ROC. Okay. So this kind of thing will be having, in this case xn, this will be minus 2 raised to n u of minus n minus 2.
Yes.
Minus 2 raised to n, yes. And this will be having z, in that case r is equal to z, so that will be having for less than 2. Now as we have drawn this case and this 2 is not a part of ROC, in this case again the ROC will come. So this is real, this is imaginary of Z, and this is the plane, and it will be inside. Okay. And this will be having this less than 2. So this 2 point, again, as this is that boundary condition that if it is there, again it will go to infinity. So apart leaving that, it will start from just inside this 2 and it will come inside the sequence.
Very good. Yes, yes, appreciate. Thank you. Thank you. Very good. That's very correct. So, not only is the region of convergence required to be specified because you need to know what Z is acceptable in the expression, it also resolves an ambiguity. That means the same expression you could associate a different region of convergence. And how do you determine the possible regions of convergence? The same principle. You look at the singularity and exclude the singularity. All the regions that can exclude the singularity are permissible as regions of convergence. But of course, one more requirement on the region of convergence, not only excluding singularity, is something which brings us to the end of what we discussed in the previous lecture. The region must be connected, right? The region must be connected, right? And now that you can think about, right? Very good. So this generalizes the discrete time Fourier transform to the Z transform. And now in the last few minutes, I would like to give you clear-cut instructions on what you will be doing in the sessions that follow, right? Now you will have 6 sessions. So we have done 10 sessions so far. You have 6 more sessions which will be conducted next week, and those will be conducted by my teaching associates. I'll soon introduce you to all of them. So are you asking, can you get back the sequence from the Z transform or from the? Yeah. Yes. Ah. Yeah. Okay, that's interesting. Yeah. So now we haven't dealt with that. What happens if you sample a Fourier transform? Isn't it? Yes. In fact, it's related to. It comes to the discrete Fourier transform, and before that, when you sample a continuous time Fourier transform, it brings you to periodic signals. So in fact, we haven't discussed all the properties of the Fourier transform. One of the properties of the Fourier transform is duality. So if you have a statement which involves the time domain and the frequency domain, the Fourier transform, there's an equivalent statement where you can reverse the roles of time and frequency, right? That's called the principle of duality. Yeah? So this principle of duality would tell you that when you sample the Fourier domain, you would get a periodic signal in the time domain, right? And of course, then if you already have sampled and taken the discrete time Fourier transform, you sample that, then you would get a periodic sequence, right? That brings you to the discrete Fourier transform, DFT, right? But we haven't dealt with that, okay? Now, anyway, the assignment for you have 6 sessions, right? Now, the teaching associates will discuss amongst you and between themselves, and you will take the 6 sessions as follows. The ordering, you can decide. Anyway, these 4 have to be ordered this way. You'll have in each of these, you'll have 4 sessions where you will do peer teaching. In the peer teaching sessions, what I want you to do is, I want you to have volunteers from among you to come and teach further topics in each module. Now, of course, those topics can, be related. So, you could decide on the topics yourself. They should teach beyond what I've taught you. And I would naturally expect that those of you who have taught the subjects before, they would want to come and take these sessions. Is that right? So I require at least 4 of you, but if there are more than 4, then what you can do is you can divide the session among yourself. Is that right? Now which of you are volunteers to teach these 4? Can you raise your hands? Very good. You have 1, 2, 3, and I need at least 1 more. Right? 1, 2, 3, and yes. Saurabh, yeah, 1 and 3. Yes, yeah, very good. 4. I think we should have at least 1 or 2 more. I think we'll request Vikash on popular demand and Shami also on popular. Is that right? We have 6 people on popular demand. Is that right? Can you all stand up, please, so everybody sees you in the class? And we should give them a big hand for volunteering. You come here, come here. All of you, yeah? Come, please come. So I'm very happy to have, yes, you can come. So the 6 of them would volunteer to teach you these 4 sessions. Is that right? And you can decide among yourself what you would like to do. Is that right? And these, and they will, you can decide how to divide between yourselves and so on and so forth. Is that right? Thank you very much. Yeah. Now the 4 sessions will be the first on module 1, the second on module 2, the third on module 3, and the fourth on module 4. What is module 1? Signals and systems in their natural domain. Is that right? In the natural domain. What is module 2? The Fourier transform. What is module 3? Sampling and reconstruction. And what is module 4? The Laplace transform and the Z transform. Does that make 4 sessions? Is that right? In the 5th session, you will have a problem posing session. You have a problem posing session. What is a problem posing session? Each group, you had formed 11 groups. Each group, 10 groups, sorry. Now, each group should come prepared with several problems which you have put together for the class to solve. And they can be based on any of the modules. And you will have different groups come and pose a problem to the class. The rest of the class must try to solve the problem. And this group must guide the rest of the class in solving the problem. Is that clear? In fact, this will occupy roughly 1.5 sessions, maybe. So it may require about, 80 to 90 minutes. Yes. Well, you should come prepared with as many problems as you can come prepared. And you can, in fact, now, these 6 people whom I just identified will be your leaders. So you will be the leaders, is that right? All of you will be the leaders in the class. And you will also orchestrate the problem posing session. And of course, my teaching associates will be behind you and they'll be guiding you. Is that right? They'll all be guiding you. Is that right? But of course, they'll, and you, by the way, the word, my teaching associates are a representative of me. So whatever my teaching associates say, you must take it as my instruction. Is that right? Yeah. The teaching. Now let me introduce my teaching associates. Come. Yeah. So they'll be looking at what you're doing. They'll be guiding you. Yes, and they'll be, yeah. Come. 2 of you can come on this side, and 2 of you can come on this side. Yeah. Yes. So I have my senior most teaching associate Harshavardhan, right? And I have Suketu Patni, I have Krunal Vagela, and I have Advay Bapat. All these 3 have actually been taught the course by me, and Harshavardhan has been a teaching associate with me when I taught the course, right? So they are very experienced. So they now, when they are conducting the sessions, their word is my word, right? So you must obey it like you would obey my word. Is that right? So yeah. So now they will guide you, and they may also pose a couple of problems. We don't know. It all depends on them, right? So this can occupy about, and of course they'll also guide you in the other sessions when you're lecturing, and they may also ask questions during those sessions. That's pretending to be students. And all of you should pretend to be students and ask questions when your peers teach you. Is that right? Very good. Thank you. So this makes 1.5 sessions. And then the 6th one, now you can 5th and 6th. The last session, you must answer the same test which you began. You must answer the same test with which you began. And I hope that this time when you answer, you will give a much better, much more comprehensive and much more, much better planned answer than you gave the first time. What was that question? You had to answer 3 questions. You had to decide the course objectives, the expected course outcomes, and the plan for achieving those outcomes in the course. Is that right? Now, this time when you answer those questions, you would have had much more experience on how to frame the course objectives, identify the course outcomes, and plan how to achieve those course outcomes. So, we will be looking at both your solution when you started and solution when you complete the module. Is that right? And my teaching associates will be reviewing both of your solutions and guiding you on them. Is that right? Yeah, that's very good. Yes. So with that, then now I leave you to the care of your very able 6 peers, right?